Hey everyone, welcome back. We're diving into something pretty crucial today, how we figure out how much water is actually going back into the ground, replenishing those aquifers we all rely on.
It's more important than people realize, right? Groundwater recharge. It's the foundation for sustainable water management. Everything from setting those pumping limits to making sure our drinking water stays safe. It all comes back to understanding how much water is actually being added back to the system.
For sure. And to get a solid grasp on this, we dug into a really heavy-hitting scientific review article. It's called, get this, The Watertable Fluctuation Method of Recharge Estimation. A review. It's kind of a mouthful, but it's published in a top journal called Advances in Water Resources. They really did a deep dive on one of the most common methods scientists use to tackle this whole recharge question.
A review like that is super valuable. It brings together decades of research, different approaches, all those nuances, really helps us cut through the noise and see the big picture of what we know and honestly what we still don't know.
Exactly. So our mission today is to unpack this water table fluctuation method, or WTFM for short. We'll break down the logic behind it, the different ways it's actually used out in the field, and where it kind of hits its limits. Plus, we'll touch on what the latest research is doing to make it even better.
And we'll do it all without getting too bogged down in the technical jargon. Promise.
Okay, so the water table fluctuation method, WTFM. I mean, it sounds a bit like something out of a sci-fi movie, right? But the core idea is actually surprisingly straightforward, isn't it?
Yeah, surprisingly. At its heart, it's about connecting the dots between what we see happening to the water level underground, like in a well, and how much water is actually seeping back into that aquifer, that underground reservoir. The key player in this whole thing is something called specific yield, often shortened to just SCI.
Specific yield.
Right. It basically tells you how much water an aquifer releases or takes in for every little change in the water table level. It's a property of the soil or rock that makes up the aquifer.
Okay, so if I'm picturing this right, if we see the water level in a well go up, say after a big rain event, and we know the specific yield of the ground around that well.
We can use a pretty simple equation to estimate how much of that rainwater actually made it down into the groundwater. The most basic formula is recharge equals specific yield multiplied by the change in water table elevation divided by the time over which that change happened.
So if the water level rose a certain amount over a week, we can plug those numbers in and get a rough idea of the recharge rate.
Exactly. And that's a big part of why this method is so popular. It's relatively simple and doesn't require tons of fancy data. You mainly need those regular measurements of the water table level and a decent estimate of the specific yield.
Which I'm guessing isn't always easy to get right.
You're right about that. Specific yield can be tricky to nail down, but we'll get into those challenges a bit later. One thing I wanted to point out is that this method has a few different names floating around.
Yeah, the review mentioned that. It can get a bit confusing if you're reading different studies.
You might see it called continuous hydrograph analysis, the groundwater accretion method, or even just the groundwater level fluctuation method. Don't let the name throw you off. They're all talking about the same core principle of using water level changes to figure out recharge.
Got it. So, same idea, different names. Now, something that stood out to me in the review was this whole net recharge versus gross recharge thing. Can you explain that in a way that, really clicks?
Absolutely. Think of net recharge as the actual increase in the amount of water stored in the aquifer. It's the final result after any water might have naturally flowed out or been discharged.
Okay, so like the net gain.
Exactly. Gross recharge, on the other hand, is the total amount of water that reaches the water table from above. From rain, snowmelt, you name it. It's like the total input. Before any losses due to natural processes like discharge into rivers or uptake by plants.
So the difference is what stays in versus the total that comes in. It's kind of like trying to fill a bathtub with the drain slightly open.
I like that analogy. The water pouring from the faucet, that's your gross recharge. But the level in the tub is only going up based on the net recharge because some is constantly going down the drain.
Right, so the water level in the tub is the result of both how much is coming in and how much is going out.
Precisely. And that's where the simplest form of WTFM, the one that just uses specific yield and the change in water level, that's where it can be a bit misleading.
Misleading how?
Well, it basically assumes that the drain is closed,
Right.
that there's no significant discharge happening while the water table is rising. So it gives you an estimate of the net increase in storage, but it might not capture the full picture of how much water actually reached the water table.
Oh, I see. So it might underestimate the total recharge because it's not accounting for the water that's simultaneously flowing out.
Exactly. And that's a problem if you're trying to build a comprehensive model of the aquifer system.
Because those models need to simulate both the inflow and the outflow, right?
They do. If you want to predict how the aquifer will respond to changes in climate, pumping, or land use, you need to know the total input, the gross recharge, to make accurate predictions.
So how do we bridge that gap? How do we go from estimating net recharge to figuring out that gross recharge number?
That's where things get a bit more complex. We have to start thinking about how to account for the water that's leaving the system, even while it's being replenished. And a key concept here is the recession curve.
Recession curve. That sounds familiar.
It's essentially a graph that shows how the water table level naturally declines over time when there's no new recharge happening. It's like watching that bathtub slowly drain after you turn off the faucet.
Right, the water level goes down because of those natural discharge processes we talked about. Okay, so how does this recession curve help us figure out gross recharge?
Well, one common technique is to take the recession curve we observed just before a recharge event started, what's called the antecedent recession curve, and project it forward in time.
Project it forward. Like, imagine how the water level would have continued to fall if it hadn't been interrupted by the new influx of water.
Exactly. We compare that projected level to the actual peak water level observed after the rain or snowmelt event. The vertical difference between those two levels gives us an estimate of the gross recharge.
Because it accounts for both the rise in water level due to the new recharge and the fact that some water was still draining out during that same period.
You got it.
Yeah.
It's like saying, okay, the water level rose this much, but it would have dropped this much if there hadn't been any recharge. So the total recharge must have been the sum of those two changes.
Yes, that makes sense. The review also mentioned a couple of different ways to project this recession curve. There's the localized recession curve, or LRC, and the master recession curve, or MRC. What's the difference between those approaches?
Think of it like this. The LRC is like focusing on the immediate weather forecast before a storm. It looks at the water level behavior right before the recharge event and uses that very recent rate of decline to predict what would have happened without the rain.
It's like saying, based on how fast the water level was dropping yesterday, we can expect it to have dropped this much by today.
Exactly. The MRC, on the other hand, is like looking at the average weather for this time of year. It tries to establish a more typical or average rate in decline by looking at many different periods of falling water levels, often encompassing multiple recharge events.
So it's more like saying, based on years of data, the water level in this aquifer tends to fall at roughly this rate when there's no new water coming in.
Precisely. So the LRC is more sensitive to those very recent conditions, while the MRC gives you a more general, long-term perspective. Which one is better really depends on the specific characteristics of the aquifer and how much data you have.
It sounds like there's no one-size-fits-all approach. The review actually talked about different flavors of WTFM tailored to fit different situations.
There are. One that's pretty interesting is called the RISE method.
RISE? What's that all about?
RISE is designed for automation. It uses frequent water level measurements, like every hour or even more often, and looks at the change over consistent, short time steps. It bypasses all that manual drawing and projecting of recession curves.
Sounds pretty efficient, but if it's automated, doesn't it also mean it's making more assumptions?
Well, it does assume that those short time steps are representative of the overall recharge process. And it doesn't explicitly account for any discharge that might be happening simultaneously. So it's essentially a net recharge method, not a gross recharge method.
Ah, so it might underestimate the total recharge, just like that basic formula we talked about earlier.
You got it. It's good for getting a quick and consistent estimate, but it might not be the most accurate if you need that gross recharge figure.
So if you really want to nail down the gross recharge, you need those methods that focus on the recession periods, those times when the water level is naturally falling.
Right. Those methods are all about carefully selecting periods where there's no rainfall or snowmelt, ideally just the natural decline of the water table. They use that data to build those localized or master recession curves.
And then use those curves to project what would have happened without the recharge so they can separate the recharge signal from the ongoing discharge.
Exactly. And the review highlighted an interesting trend. There's a shift away from those manual graphical methods, drawing lines on graphs, towards using mathematical functions to fit those curves. Exponential functions are super common because they often capture that gradual decay of groundwater levels pretty well.
I can see how that would be more precise and less subjective. Now, what about that episodic master recession EMR
Oh,
approach?
that's a clever one. It takes the master recession curve and applies it to individual recharge events, like those distinct peaks you see in the water level data after a storm. It uses the MRC to account for both the discharge happening during the water level rise and something called overshoot.
Overshoot, what's that?
It's basically a temporary rise in the water table that might not be caused by actual recharge, by water infiltrating from the surface. It could be due to things like changes in air pressure, temperature fluctuations, or even something called the Liss effect.
Bliss effect. Okay, now you're just making up words.
No, it's a real thing. It happens when intense rainfall traps pockets of air in the unsaturated zone, that layer above the water table. That trapped air can cause the water level to jump up quickly, but it's not really due to new water being added to the aquifer.
So it's kind of a false signal.
Yeah, exactly. And the EMR method tries to filter out those false signals to get a cleaner estimate of the actual recharge from that specific event. It uses the MRC to project the water level both forward from the start of the rise and backward from the peak, basically trying to isolate the part of the change that's truly due to recharge.
Clever. But it still seems like there's a lot of room for error, with all these different methods and the inherent complexity of what's happening underground.
Oh, absolutely.
Wow.
And that brings us to one of the biggest elephants in the room with WTFM uncertainty. The review made it very clear that we have to acknowledge and try to quantify this uncertainty if we want to use this method responsibly.
Where does most of that uncertainty come from? Is it all those assumptions we talked about?
It's partly that, but a major culprit is specific yield. Remember, that's the property that tells us how much water the aquifer releases for a given change in water level.
Right, the key ingredient in that basic formula.
Exactly. The problem is that specific yield isn't a fixed value. It can vary a lot depending on the geology, the depth, even the history of water level changes in that area. And it's notoriously difficult to measure accurately, especially in complex environments like fractured rock.
So if our estimate of specific yield is off, our estimate of recharge is probably off too.
By potentially a large amount, yes. And that's not the only source of uncertainty. The assumptions we make about how recharge happens can also introduce errors, like that basic formula, assuming all the recharge is coming from directly above the well.
Right. But in reality, water can flow laterally underground, and there can be all sorts of interactions with nearby rivers and lakes.
Exactly. And then there's the quality of our data. How often are we actually measuring the water levels? Are our measurements accurate? Even small errors can add up over time. And the method we choose for projecting that recession curve, that also adds another layer of uncertainty.
So it's like a chain of potential errors, each one potentially affecting the final result. It makes you wonder how much confidence we can really have in some of these recharge estimates.
It's a valid concern. That's why researchers are working hard to develop ways to better quantify this uncertainty. Some approaches use a range of possible values for specific yield, kind of like saying, okay, we think the specific yield is somewhere between this value and that value, so let's see how that affects the recharge estimate.
So instead of just a single number, you get a range of possibilities, which gives you a sense of how much uncertainty there is.
Exactly. Another approach is to compare WTFM results to those obtained from completely different recharge estimation methods. If they agree, that gives you more confidence. If they disagree wildly, well, that's a red flag that something might be off.
It's like getting a second opinion from a different doctor. Speaking of those other methods, how does WTFM stack up against the competition?
There are quite a few alternatives out there, like the chloride mass balance method, catchment water balance studies, bathymeter measurements, soil moisture modeling, even groundwater age dating. Each one has its own strengths and weaknesses, its own set of assumptions.
And when you compare them head to head,
The results are a bit of a mixed bag. Sometimes they agree, sometimes they don't. Interestingly, when there were discrepancies, WTFM often gave higher recharge estimates than the other methods.
higher. Why would that be?
It could be because of those assumptions we talked about, or it could be because WTFM is more sensitive to short-term variations, while some other methods give you a longer-term average. It's not always clear-cut.
So it's not like one method is always better than the others. It sounds like it really depends on the specific situation and what you're trying to achieve.
Precisely. Using multiple methods and comparing the results is often the best way to get a more complete and reliable picture of the recharge process. It's like using different tools to solve a complex puzzle.
So even with all these limitations and uncertainties, WTFM is still a valuable tool. The review made it clear that there's a lot of ongoing research to try and address those shortcomings and make it even better. What are some of the key advancements that are being made?
Researchers are getting pretty creative. For example, they're developing modified versions of WTFM for aquifers with deep unsaturated zones, where the water has to travel a long way before reaching the water table.
So the classic WTFM, assuming a quick response, wouldn't work so well in those cases.
Right. And there are adaptations for places where recharge is more continuous, rather than just happening in distinct events. And for shallow water table aquifers, where specific yield behaves differently, they're even tackling those tricky fractured rock aquifers, trying to account for how specific yield can change with depth in those complex environments.
What about the impact of pumping? It seems like that would be a huge factor in many aquifers.
Absolutely. And there are efforts to incorporate pumping directly into the WTFM calculations rather than just excluding data from wells near pumping centers. There's also work on interpreting data from wells near rivers and lakes, where the water levels might be influenced by both surface water and groundwater, and even ways to try and filter out that List effect we talked about to avoid those false positives.
It's like they're constantly tweaking and refining the method to handle all these real-world complexities. But the review did caution that many of these modifications still need more testing and validation.
That's a crucial point. We need to make sure these new approaches actually improve the accuracy and reliability of the estimates. The review suggested using synthetic data from computer models or controlled field experiments to rigorously test these methods and see how they perform under different conditions.
So basically, put them through their paces in a controlled environment where you know the actual recharge rates.
Exactly. That way, you can see how well they capture the real-world processes. And beyond just improving the method itself, there are other big research questions that need to be addressed. Like, what spatial scale does a WTFM estimate from a single well actually represent? How do we upscale those local estimates to get a regional picture?
So it's not just about measuring at one point, it's about understanding how that point fits into the bigger picture.
Right. And there's still debate about the best way to analyze and project those recession curves. A deeper understanding of the factors that control recession behavior would be huge. And integrating WTFM with other types of data and models like hydrochemical data or groundwater flow models, that's another exciting area of research. It's about combining different perspectives to get a more holistic view of the recharge process.
It's incredible to think about all the complexity hidden beneath something as seemingly simple as watching water levels in a well. So, as we wrap up our deep dive today, what's the key takeaway about the water table fluctuation method?
It's a powerful tool, no doubt, but it's not a magic bullet. It has its limitations, its uncertainties. That simple formula can be a bit misleading if you don't understand the underlying assumptions and the potential sources of error.
So it's important to be critical of those recharge estimates to understand where they come from and what they might be missing.
Absolutely. And when you consider how vital groundwater is for so many of us, how we rely on these methods to understand its replenishment, it really highlights the need for ongoing research and for using multiple lines of evidence when making decisions about water management.
Couldn't agree more. It makes you think about all the other seemingly straightforward environmental measurements that might have similar hidden complexities. Thanks for taking this deep dive with us today. This was eye-opening.
My pleasure. Always happy to delve into the intricacies of groundwater.
Until next time, folks, keep those questions coming. We'll keep digging for those essential insights.
And remember, even when it seems simple, there's often a lot more going on beneath the surface.